What are neutron stars and how are they formed? Neutron stars are the densest objects in the universe, with masses up to twice that of the Sun packed into a space the size of a city. To understand how they are formed, we first need to look at the life cycle of a massive star. Massive stars, which are several times more massive than the Sun, go through a series of fusion reactions in their cores, converting lighter elements into heavier ones. These reactions produce energy that keeps the star from collapsing under its own gravity. However, at the end of their lives, massive stars run out of fuel and can no longer generate enough energy to support themselves. Without this energy, the outer layers of the star collapse inward, triggering a catastrophic explosion known as a supernova. During a supernova, the star's core collapses in on itself, creating a dense object made almost entirely of neutrons called a neutron star. To put this in perspective, imagine squeezing the mass of two suns into a sphere with a diameter of only 20 kilometers. This extreme compression causes the neutrons to be packed so tightly that they are only a few kilometers apart, creating an object with an incredibly strong gravitational field. But how exactly do we know that neutron stars exist? Well, one way is through their effects on nearby matter. Neutron stars have extremely strong magnetic fields, and they can pull matter from nearby stars, creating a disk of hot gas that emits X-rays. Astronomers can use X-ray telescopes to detect these emissions and study the properties of neutron stars. Supernovae are some of the most energetic explosions in the universe. They occur when a massive star exhausts all of its fuel and can no longer support itself against the force of gravity. The star's core collapses under its own weight, creating a dense, hot ball of matter that rapidly rebounds outward in a catastrophic explosion. But supernovae are not just destructive events. They also play a crucial role in the formation of neutron stars. When a massive star collapses, its outer layers are blown away, leaving behind a compact core made up of neutrons, protons, and electrons. The intense gravitational forces in the core of the star cause the electrons and protons to combine, forming neutrons through a process known as electron capture. This process releases a large amount of energy and leads to the formation of a neutron-rich core. The core of the star then undergoes a process known as gravitational collapse, in which the intense gravitational forces compress the core to a size of only a few kilometers. This leads to the formation of a neutron star, which is incredibly dense and has a strong gravitational field. So why are neutron stars so interesting to scientists? Well, neutron stars are some of the most extreme objects in the universe, and studying them can tell us about the fundamental properties of matter and the behavior of matter under extreme conditions. In addition, neutron stars have a number of unique properties that make them valuable for studying other phenomena in the universe. For example, the strong magnetic fields of neutron stars can be used to study the properties of matter in the universe, and the intense gravitational forces near neutron stars can be used to study the nature of spacetime itself. Pulsars are a special type of neutron star that emit beams of electromagnetic radiation from their magnetic poles, much like a lighthouse emits beams of light. These beams of radiation are extremely regular and can be detected by telescopes on Earth as pulses of light. One of the most striking properties of pulsars is their incredibly high rotation rates. Pulsars can spin hundreds of times per second, making them some of the fastest spinning objects in the universe. This high rotation rate is thought to be a consequence of the conservation of angular momentum during the collapse of the original star into a neutron star. But why do pulsars emit these beams of radiation? Well, the answer has to do with their strong magnetic fields. Neutron stars, including pulsars, have incredibly strong magnetic fields that can be trillions of times stronger than the magnetic field of the Earth. As the pulsar rotates, its magnetic field generates powerful electric currents that accelerate particles in the pulsar's magnetosphere, causing them to emit beams of radiation from the magnetic poles. These beams of radiation sweep across the sky like the light from a lighthouse, producing the regular pulses that we observe from pulsars. The properties of pulsars are closely related to those of neutron stars, since pulsars are simply a special type of neutron star. In fact, many neutron stars are thought to be pulsars that are oriented in such a way that their beams of radiation are not visible from Earth. Studying pulsars and neutron stars can tell us a great deal about the behavior of matter under extreme conditions, such as the properties of extremely dense matter and the behavior of magnetic fields in the universe. In addition, Pulsars and neutron stars can be used as natural laboratories for testing the laws of physics under extreme conditions, such as the theory of general relativity. Gravitational waves are ripples in the fabric of space-time that are produced by the acceleration of massive objects. They were predicted by Albert Einstein's theory of general relativity, but were not detected directly until 2015. In August 2017, scientists detected a gravitational wave signal from the collision of two neutron stars, which are some of the most extreme objects in the universe. This detection was made possible by the Laser Interferometer Gravitational Wave Observatory and the Virgo Gravitational Wave Detector. The detection of this gravitational wave signal was an exciting development for several reasons. First, it provided the first direct evidence of the existence of neutron-star collisions, which had been predicted by astrophysicists for decades, but had never been observed before. In addition, the detection of this signal provided important insights into the origin of heavy elements in the universe. Neutron-star collisions are thought to be one of the primary sources of heavy elements, such as gold, platinum, and uranium. During a neutron-star collision, the extreme temperatures and pressures create the conditions necessary for the formation of these heavy elements. The collision also generates a burst of energetic particles, known as a kilonova, which can be detected by telescopes on Earth. The detection of the gravitational wave signal from the neutron-star collision was followed by observations of the kilonova by telescopes around the world. These observations confirmed the production of heavy elements in the collision and provided important information about the nature of these elements. One of the most common techniques is radio astronomy. Radio telescopes can detect the radio waves emitted by pulsars, which are among the most powerful radio sources in the sky. By analyzing the timing and characteristics of these radio waves, astronomers can learn a great deal about the properties of pulsars, such as their rotation rates and magnetic fields. Another technique used to study neutron stars and pulsars is X-ray astronomy. X-ray telescopes can detect the X-rays emitted by these objects, which are produced by the incredibly hot and energetic environments around them. By studying the X-rays emitted by neutron stars and pulsars, astronomers can learn about the properties of their surfaces, as well as the behavior of the surrounding gas and dust. In addition to radio and X-ray astronomy, astronomers also use optical telescopes to study neutron stars and pulsars. Optical telescopes can detect the light emitted by these objects, which can provide important information about their temperatures, compositions, and environments. However, optical telescopes are typically less useful for studying pulsars than radio or X-ray telescopes, as the light emitted by pulsars in the visible range is often very faint. Finally, astronomers also use a variety of other techniques to study neutron stars and pulsars, such as gamma-ray astronomy, neutrino astronomy, and gravitational wave astronomy. Each of these techniques provides a unique perspective on these objects and can help astronomers to better understand their properties and behaviors. Thank you for joining us on this journey through the fascinating world of neutron stars and pulsars. We hope you found this video informative, engaging, and awe-inspiring. Remember, the universe is full of wonders waiting to be discovered, and we're thrilled to have been able to share just a small piece of it with you. Keep exploring, keep learning, and keep marveling at the incredible mysteries of the cosmos. Thank you for watching.